Our story begins briefly 2,300 years ago with Euclid of Alexandria, who laid the foundations of our understanding of space. In Euclidean geometry, space is flat, which means that all triangles, no matter how large, have angles that add up to pi radians. A very important concept in our story will be the notion of distance between 2 points. The mathematical object that describes distances in flat Euclidean space is called the Euclidean metric. Fast forward 2,000 years, where young Isaac realized that the fundamental reason why the apple fell at Woolsthorpe Manor was in fact due to the same fundamental force that held the celestial bodies in their orbits around the Earth. Together with his newly developed mathematical theory of calculus, he could formulate his law of universal gravitation. It took 300 years until anybody could challenge the notions of Euclidean space and Newtonian gravity. But then, in 1905, a brilliant young man realized that if the speed of light was indeed constant, as was indicated by Maxwell's theories, and if the laws of physics would be the same in all inertial reference frames, the principle of relativity, then we would have to abandon concepts like absolute space and absolute time, and even the idea of absolute chronology of events in the universe. Different observers would measure these quantities differently depending on their relative velocities. To make order out of this chaos, Einstein and Minkowski unified space and time into a four-dimensional manifold called space-time. In this mathematical space, Minkowski space, the distances between events is calculated by the Minkowski metric, and it gives the space-time interval, a quantity that would finally be the same for every observer. Special relativity deals mostly with inertial reference frames, namely unaccelerated systems. But in the time after the 1905 publication, he came to another great realization, that there was no way for an observer to distinguish if he or she were in a non-inertial or accelerated reference frame, or simply standing on a massive body under the influence of gravity. This is the equivalence principle. It took 10 years for Einstein to fully develop this theory. In this time, he realized that also gravity would need to be integrated into space-time, and in 1915 he published his fully developed theory of general relativity. General relativity is a theory which relates the energy and matter content in the universe to the curvature of space-time, and the fundamental equation in this theory is the Einstein field equation, which looks like this. G mu nu is the Einstein tensor, and it encodes the information we know about the curvature of spacetime. It depends on the metric and its derivatives. On the right-hand side, we have T mu nu, which is the energy momentum tensor, and it is a measure of the energy content in spacetime. Finally, we have on the left-hand side the big lambda, which is the cosmological constant, which is the value of the energy density of the vacuum of space, and it was introduced by Einstein to hold back gravity in order for him to find static solutions to the field equations. Later, in 1929, when Edwin Hubble demonstrated the linear redshift distance relation from the light coming from distant galaxies, Einstein was forced to abandon the notion of a cosmological constant, famously calling it his biggest blunder. Now, the first man to find a non-static solution to Einstein's field equations were the Russian physicist Alexander Friedmann. To solve the field equation, Friedmann used the cosmological principle. The cosmological principle is the assumption that while on small scales the universe is quite complicated to describe, there's stars and galaxies here and there and mostly nothing in between. But on large enough scales the universe is in fact very simple. It is homogeneous, meaning that if you were to select a volume of space at random, it would contain the same stuff as if you were to select any other volume. And also, the universe is isotropic, meaning that it looks the same in no matter which direction you look. Now, the metric to describe distances in an homogeneous and isotropic universe is the Friedmann-Lemaitre-Robertson-Walker metric. This metric contains the familiar time part, but the spatial part is written as a scale factor A times sigma, which is some three-dimensional space which can have either positive, negative, or zero curvature, depending on the curvature parameter k. Now, it is notoriously hard to think intuitively about curved three-dimensional spaces, and to get a sense of what this means, let us instead consider a curved two-dimensional space. If the two-dimensional surface has zero curvature, then it is Euclidean, but if it has positive curvature, then the sum of all triangles no longer add up to pi radians. For a surface with positive curvature, they add up to more, and for a surface with negative curvature, they add up to less. These surfaces are non-Euclidean, and in general relativity, empty space can be non-Euclidean with either positive, negative, or zero three-dimensional curvature, depending on the density within the universe. Friedman used the Robertson-Walker metric to solve Einstein's field equations to get an equation relating the rate of change of the scale factor to the density of the universe and its global curvature, the Friedman equations. I'm told that the full relativistic derivation of the Friedman equation is both laborious and not very illuminating, but luckily we can do without. We will now derive the Friedman equations using only Newtonian gravity. It goes something like this. Imagine a sphere inside the universe of an arbitrary radius r. Now, the gravitational acceleration at any point on the surface of the sphere is given by Newton's law of gravity. We can write the mass inside the sphere as a volume times some density function. Now we need to turn Newton's equation into an energy equation. We know that energy is force times distance, so let's integrate with respect to r. The right-hand side is easy. It just gives minus the gravitational potential energy at the surface of the sphere. For the left-hand side, we use a nice little trick where we write dr equals dr dt, and then we realize that the integrand is in fact the total time derivative of the kinetic energy, making it super easy to integrate. Thus we end up with the energy equation where U is a constant of integration, but we know we can physically interpret it as the total energy per unit mass as the surface of the sphere. Now let's plug in the expression for the mass and write the radius as some constant radius times a scale factor. We end up with this equation. And finally, dividing by r squared, a squared over 2, we end up with the Friedman equation. To write the equation in the correct form of general relativity, we just make the association that the integration constant u is in fact proportional to the curvature parameter from the Robertson-Walker metric, and the real equation looks like this. It's hard to overstate the importance of the Friedman equation for cosmology. From the Friedman equation, we immediately get the Hubble parameter, which is simply a dot over a. And we see that the expansion of the universe can in fact vary with time depending on the energy content and curvature of the universe. Another important quantity we can derive from the Friedman equation is the critical density. If we set k equals to 0 in the Friedman equation, then the density becomes proportional to the Hubble parameter. This critical density is the density the universe would need to have in order to be flat or Euclidean. If the density of the universe is larger than the critical density, then the universe will have positive curvature and the universe will eventually stop expanding and then recollapse. If the density of the universe is less than the critical density, then the universe will expand forever. And finally, if the density of the universe is equal to the critical density, then the universe will expand forever, but at a continuously decelerating rate. Now, the actual value of the critical density is very small. It's something like 10 to the 26 kilogram per cubic meter, which is something like 6 hydrogen atoms per cubic meter. It is customary to introduce the density parameter omega as the density divided by the critical density. At present, we know that we must add up all forms of energy to get the total density parameter for the universe. The different contributions for the total density parameter comes from normal matter and the effective mass from relativistic particles, that is photons and neutrinos, and together with what we now hypothesize as dark energy. In 2003, the Wilkinson Microwave Anisotropy Probe conducted a detailed survey of the cosmic microwave background, which enabled physicists to calculate the contributions from different forms of energy at present time. Remarkably, the result for the density parameter is 1.02 plus or minus 0.2. And thus the density at present time, if not exactly equal, then it's very close to the critical density. This means that with our present knowledge, our universe seems to be flat. It seems we are living in a Euclidean universe after all.